Okay, Chemistry 3111. I wanted to take a look at some questions that involve Birch reduction with you. So this is question 17.0.20 rather. And the conditions for Birch reduction, so Birch, and it's named after somebody named Birch reduction, are to take an aromatic compound, treat it with sodium, methanol, and ammonia, and we're going to end up with some derivative of 1,4-cyclohexadiene, right? Something like this. But since we've got this isopropyl group on here, we have to take regioselectivity into account. Now, what you have to remember is that since the isopropyl group is an electron donating group, an EDG, electron donating by or via hyperconjugation, that we are not going to reduce the carbon where the isopropyl group is attached. And so what we're going to end up with is just draw the 6-membered ring like this. And there's a couple of ways you could draw it. You could put the double bond here like this and this. So there's our 1,4-cyclohexadiene derivative. Or if you wanted to write it like this, right? If you wanted to put the isopropyl group here and put it like this and like this. Either way, it's the same, essentially the same thing, okay, is what you're getting. Remember, the idea is that you can't reduce this carbon because we have an electron donating group there. Now, the next two are a little more interesting because now we've got two electron donating groups, don't we? In B, we have the isopropyl group, which is an electron donating group, and we have a methyl, which is electron donating, and they're para, right? The substitution is para substitution. So if we draw the 6-membered ring, again, we're treating it with sodium, methanol, and ammonia. Let me draw my 6-membered ring like that. I'll put the isopropyl group over here. I'll put the methyl group here like this. Well, we've got to make sure we've got a double bond on that carbon and we've got a double bond on that carbon. How are we going to do that? We could either write it like this, okay, like this, or we could, just bear with me here, my isopropyl and my methyl, or we could have written this. Either one is correct, okay? They're essentially the same thing, all right? They are the same thing. Anyhow, let's move on from there. Now, the next one I think is a little more interesting because you've got two electron donating groups, except now they're meta-substituted, aren't they, right? I've got, again, an electron donating group, an EDG. I've got another one here, but the substitution is meta, so that when I draw my aromatic ring, okay, and if I put my isopropyl here and my methyl group here, I can't reduce this one or this one. Those two carbons have to have a double bond. So you see that if I did this, and this is wrong, but if I put the double bond here, then I'd be in trouble because then I have a double bond here, and that means that carbon is reduced. So that is wrong. The way I've got it is wrong. The correct way would be to put the double bond here and here. Now I ensure that both of those carbons remain in the same oxidation state. Neither of them gets reduced. All right. Let's see here. Let's take a look at D. So moving on to D. Or I just have to get my textbook in the right place so I can see D. D is this compound. So I've got, really, they're moving this methyl and isopropyl. They're migrating the methyl all over the ring, aren't they? Right. So here we go. We've got sodium. We've got methanol. We've got our ammonia in there, and then I'm going to reduce that. But now I just want to ensure that I don't reduce which carbons. I'll highlight them in yellow again. So the only way to draw it would be like this and this. All right, let's take a look at E. So move down to E. I've got what? Benzoic acid. Well, this one shouldn't take us that long to do. I'm not interested in rushing in organic chemistry. I don't like rushing. But I think you should be able to solve this one relatively quickly because we know that we are going to reduce this carbon, right? The one that I have in the circle or the one that I'm highlighting in yellow, we will reduce that carbon. And so the reason why we reduce that is you have to go back and look at the mechanism, and you're going to end up with an anion there at some point, but you've got an electron withdrawing group, right? This is an electron withdrawing group, so it sucks away some of that negative density and it stabilizes that transition state. And that is why that carbon is going to end up getting reduced. And so we'll redraw our 6-membered ring. We'll put our carboxyl group like this, okay? And then we'll put our double bonds here and here. And then for the last one, F, we've got an electron withdrawing group and an electron donating group on the same molecule. So we've got an isopropyl over here, which is electron donating, okay? So let's see. I know that I want to, or I don't want to reduce this one. However, I do want to reduce that one. So what are our options? You've only got one option in this case for a regioisomer. And so let's draw the reagents. After you've done this problem, you'll have these memorized, won't you? Sodium, methanol, and ammonia. Okay. We'll draw our 6-membered ring. Like that. We put our isopropyl group here. That carbon is not going to, that carbon is not going to get reduced. And then the carboxyl group is over here. And that carbon is going to get reduced. And so there you go. That's our only possible regioisomer. And so again, what's the difference here is that now you had an electron withdrawing group and an electron donating group at the same time. And so again, it's regioselectivity you've got to be concerned with. You see how in C, D, E, and F, we only ended up with the one possible way. And then in A and B, I mean, you're just drawing the same molecule a different way, but you see how you can kind of like reduce the bonds 2 different ways, even though you're getting the same molecule no matter what. These 2 are identical, and these 2 are identical. There we go.